Singularity.
My name is Nicola, aka Socrates, and you're watching Singularity One-on-One. Singularity One-on-One is a regular podcast feature of Singularity weblog, where you can go and listen to it or download it in full. If you guys enjoy this show and you want to help me make it better, you can do so in several ways. You can write a brief review for it on iTunes. You can click the like button on YouTube, or you can simply make a donation. And as always, I will be the man with the questions. And today, the person with the answers is Geordie Rose. Dr. Geordie Rose is a founder and chief technology officer at D-Wave Computers, which is the first company in the world that sells quantum computers. Their most recent customers, their most recent computer was actually bought by Google and NASA, and that deal made headlines around the world. So without further ado, hi Geordie, and thanks so much for being with us today.
Hi, it's great to be here. I know I have some big footsteps to follow, and I know that a lot of the people that you've interviewed are very interesting, and hopefully I can hold up my end of the bargain.
Oh, thank you very much, Geordie. I think you're overestimating me and underestimating yourself a lot. But I do appreciate that. So let me jump in by asking you first, if you were to introduce yourself and what you do in a couple of sentences, how would you do so?
Well, I founded a company that is attempting to build a new kind of computer. And the types of computers that we're building, the intent is to try to use all of the most recent information about physics and computer science to attempt to build computers at the limits of what physics and computer science, which is kind of a branch of physics, allow. So our intent for this project, although it became one that was focused on the quantum computing aspect of computers, the vision is quite a bit bigger than that. The vision is to initiate an entirely new type of organization that builds processors to the extent that they can be, the most effective, efficient tools possible, subject to still obeying the laws of physics. Mm-hmm. But it just turns out that using quantum mechanics to try to accelerate computation is an idea that has a lot of merit, and normal computers that we're used to now are not architected in a way to be able to do this if you continue to evolve them in the directions that they're going. So we decided to make to create an effort to change the underlying architecture of the computer to make it easier or possible, I suppose, to try to harness these wonderful effects and thereby get phenomenal advances in computing power for very important problems.
Mm-hmm. Now, I will definitely come back to the von Neumann traditional architecture and ask you on how and why you're different from it. But before we get there, I want to ask, first of all, a few more questions about you personally. And that is, how did you get interested in physics in general and in quantum computation in particular, or in quantum computers in particular, and why? What's so amazing about it that inspired you so much?
So when I went to university at first, the area I was in engineering and something called engineering physics, which is, broadly speaking, engineering where you take a course from all of the different disciplines. You know, you take one from civil and one from metallurgy and all of these sorts of things. And in the course of doing that degree, I was also wrestling for the university team. And there's this peculiarity in Canada that you can wrestle for a university team for 5 years. So you have 5 years of eligibility, but the course was only 4 years long. So what I ended up doing so that I could use up all my eligibility was I took a break from the engineering physics curriculum and did a year of nothing but the courses that I thought sounded the coolest in the catalog. You know, you get the undergrad catalog. And so the ones that I thought sounded the coolest were all math and physics courses, like special relativity and general relativity and all these advanced topics in math, like, algebraic geometry. And I didn't even know what it was, but it sounded really cool. So I spent a year doing nothing but advanced physics and math courses, which I kind of was allowed to do. I don't exactly remember the details, but they let me take a 1-year hiatus from the degree, and I took all this advanced stuff. And it was everything that I hoped it would be. So when you learn about advanced physics kinds of things like quantum mechanics and special relativity, it's kind of mind-blowing. I think it appeals to a certain kind of mindset that, you want to understand big things about the universe. You don't so much care about what's going to be in this paper tomorrow, but you really care about what the fabric of space-time looks like. So I'm always being a little bit like that. I want to understand the way things are to the extent I can. And so physics appealed to me. And the math was also very, very interesting because I had it in my mind that maybe I would become a mathematician, because math is somehow pure and abstracted away from the messiness of reality. And it became very clear during that 1-year hiatus that I was never going to be a mathematician, because I don't have the mind for it. There's some people have the ability to think in a way that's consistent with advanced mathematics, either by doing algebra, which is the way most people do math, or by thinking in pictures and concepts, which some other people do. And I can do a little bit of both, but I'm not at the level of like a professional in either. So I realized I was going to be a mathematician. So after that, I decided I wanted to go into physics. So I applied to a bunch of schools for theoretical physics, and I got into a bunch of them and decided I wanted to go to UBC. So I enrolled in the theoretical physics program there, and during the course of my studies, began to concentrate more and more on condensed matter physics, to study the materials at low temperatures. And part of the reason for that, a lot of physics is a little bit abstracted from the ability to test the theories. So if you become a string theorist, one of the problems in that field is how do you know whether you're right? And in solid state physics, when you're thinking about materials, it's very easy usually to do an experiment to test whether you're doing makes sense. And the particular area that I was interested in was the borderline between quantum mechanics and classical physics, because even to this day, it's very poorly understood how they remain compatible with each other. I think that people think that problem is resolved more than it is. Speaking as somebody who's been working in the borderline between the two professionally for almost 15 years, and before that, even longer in school, I can tell you with 100% certainty that there are a lot of mysteries about the way that the classical world comes from the quantum mechanical world. And also, maybe even a more important question is, what does the quantum mechanical world that we understand, what does it mean? These ideas about what is the ontological nature of reality, what is actually there, is not clear from the formulation of quantum mechanics as it currently stands. There's something missing, I think. It may be a big thing missing from our understanding of that. So I was fascinated by this. But during my time in grad school, I had another one of these revelations that I was never going to be a professional physicist, because I wasn't nearly as proficient at it as my colleagues. So I was in this interesting position of being absolutely fascinated by quantum mechanics and physics and what you could build in the universe and what it all meant. But I didn't really feel like I had the mental horsepower to delve deeply into these things and answer these questions myself. So I started thinking about how I could have both, be involved in these big ideas, but not as their practitioner. And about at that time, I took a course in the UBC Business School. And the idea of the course was to bring in half of the class from the MBA program and half of it from the sciences and engineering, and then bring in people who'd been successful in startup environments to talk to the course. And then ultimately we put together a business plan and sort of learned by doing. And that was when I knew I'd found my calling, because the idea of being able to build teams of people to tackle big problems and marshal all of the resources that are required to do so. That I finally found the thing that was the sweet spot for me. I was never going to be a mathematician or a physicist, but this was something that I felt that I could be world class in, and I then committed myself to this particular project, which was about building computers at the limits of physics and computer science. And that was roughly 15 years ago, and it's been a long, hard battle, a lot of trials and tribulations along the way, but I think it's pretty much worked out the way we thought it would.
So if I get it, you decided to be an entrepreneur.
Yeah, that's right. Although I would say that what it means to be an entrepreneur isn't always clear. You know, in modern parlance, an entrepreneur is somebody who attempts to develop profit from the sale of product in a quick period of time without raising a lot of money. My entrepreneurial instincts are more about the development of fundamentally new technologies. So I feel like there is an overemphasis on the fast monetization of new ideas, and there's a niche for the role that used to be played by corporate research labs, like the Bell Labs and the Xerox parks, that's no longer being played. So there's this gap in this is a very important point, and I think that if there's one thing I can tell your listeners about D-Wave and why it's been successful, it's this point, that university research in basic science is optimized around a process that takes 1 to 4 years, which is the time in which you have your students or postdocs, and budgets that are on the order of a few $100,000, because that's typically what you have access to as a university researcher. And the process works great if you're in that kind of area. If you're attacking a problem that requires an order of magnitude, either more money or time, university researchers are simply unable to attempt it. And building quantum computers or fusion reactors or artificial intelligence, human style cognition, these big ideas are not within the scope of the modern university research environment to attack effectively. And so you can ask, well, who is doing these things? And the answer really is nobody is doing them right, because they used to be done right back when they were done in the IBM researches and things like this. But nowadays, this whole business is being de-emphasized in terms of in favor of these incremental, short-term modifications of existing stuff. So for me, my flavor of entrepreneurship is kind of the Elon Musk flavor of entrepreneurship, or maybe the Craig Venter flavor. What I want to do is create something fundamentally different. And then once you've done that, assuming that it's important and has value, then you figure out how to productize it. And so in quantum computing, the first and foremost task, which took quite a long time, was to build the underlying technology to the point where it could compete with conventional machines. The actual productization of it is a whole other matter. It's not that it's easier or harder. It's just different. And so my interests lie in that early formative stage. How do you create something that wasn't there before in the technology space and not necessarily in the business space? I could leave that to somebody else to figure out.
Now, before we jump again into those, I have a couple of more questions here. What happened with your wrestling career? I mean, I can see how wrestling can become very useful in wrestling with the business problems and sort of setting up a team and all the obstacles that you face on the way. But how about the on-the-mat stuff? I mean, I'm Bulgarian. We were famous for some of the best wrestlers in the world. So what happened?
Well, I've always loved sports of all sorts. And I actually like football more than wrestling. But for reasons that had to do with where we lived and the quality of the programs, football became not an option for me to pursue. I probably never would have been any good at it at a high level anyway, but it was I preferred it in terms of how fun it was. But so of all the sports I did, the one that I was best at was wrestling. So I ended up focusing on it. And it was a big part of my life. In fact, I think it was the dominant part of my life for most of my university career, at least in my undergrad side and in high school. And I grew to love it, and all my circle of friends were from the wrestling side of things. So in university, the only people I hung out with were the wrestlers. I didn't hang out with the people in my own class because I had a lot more in common with the wrestling folks. But what eventually happened is, I think what happens to everybody who's a competitive athlete, you become old. And the age takes its toll in a couple of ways. One, it takes its toll physically. You're unable to train as hard as you used to be able to. But it also takes its toll in the increase of responsibilities and the other things in your life that need attention. So when you start a startup, you're working a lot. And that makes it so that it's much more difficult to fit in the other things that you care about. So right now I try to strike a balance. I still do recreational Brazilian Jiu-Jitsu, which is kind of like soft wrestling. It's like it's more like yoga, like assisted yoga. Somebody's put your leg behind you.
I love how you describe Brazilian Jiu-Jitsu as soft wrestling.
Having done both at a fairly high competitive level, there's really no comparison between the two. I mean, maybe I'll get in trouble for my for saying this, but the reason that's true is that there are a lot more people who wrestle. And it's an Olympic sport, or at least hopefully it will be an Olympic sport. There's a much longer culture to the competition side of it, and like any other sport, how hard it is at the top is a function of how many people feed in at the bottom. The more people do something, the harder it is at the top because of the whole, genetic spread of capability and the Six Sigma thing, right? Mm-hmm. So if you wanted to pick the hardest sports in the world, they're the ones that the most people play. I mean, that's just a fact. So wrestling, it breeds a type of mentality and athlete that I think is unique in all of sports. It's an interesting thing because wrestling is the hardest sport divided by the least recognition. So if you had a ratio of hardness divided by recognition that you get, future prospects of being a professional, it's the lowest of anything you could possibly imagine. Than like the javelin toss. It's just not going to ever land you anything, but it's very, very, very hard to compete at a high level. Whereas Brazilian Jiu-Jitsu, just to give you an anecdotal thing, I basically stepped on I did a bunch of Brazilian Jiu-Jitsu tournaments without training at all, and I won them all. And the reason was the wrestling, right? If you can, we're getting a little off topic here, so I can go on. But wrestling is a fundamental base for all competitive sports. I think you could take a competitive Olympic level wrestler and they could win a karate tournament. It's just the way that people train and the way they think and the will that you get. In a lot of combative sports and maybe in all sports, persistence in the face of adversity is one of the things that differentiates people at the top. And in wrestling, if you don't have that, you're never going to even win a high school tournament. So it's one of the things that you get from it.
Yeah, I personally know a number of former top-notch wrestlers, both at the Olympic and at the world level, and based on my conversations with them, I think they would absolutely back what you just said. Which, by the way, is not a popular opinion. It's kind of like the minority, I think. Anyway, let's get back to topic here, and let me ask you this. What does the name D-Wave stand for?
The original founding of the company was based on the idea of pursuing a qubit, which is sort of the fundamental unit of a machine that was built out of something called a D-Wave superconductor. D-Wave superconductor is, it's kind of a long story, but in the late 80s, there were a class of materials discovered, the cuprate superconductors. YBCO is usually the first one, that had a transition temperature where they became superconducting at fairly high temperatures, liquid nitrogen temperatures. And this qubit was a design that was based on using those materials as a substrate. it ended up being one of the worst ideas that had ever been generated in the history of our company, and we've had some doozies. So it's kind of a little bit of an inside joke that, there will be bad ideas along the way, but you can survive survive a bad idea if you have 9 good ones.
Yeah. And what's the ultimate goal of D-Wave? What's like the dream, the vision?
Well, I think it's related to the stuff that I was talking about in the intro, that it's our strong belief that as computing technology matures, you're going to reach points where the problems that are still outside of the scope of the conventional approaches are going to be too far outside of the scope of those conventional approaches to get to using them. If that's true, then there's a role to play in the world for different types of computers that operate using different physical principles that attack those problems. And if that's true, we know that there are big opportunities to both sell and use systems like that. And ultimately, what I believe is that the great-great-great-grandchildren of the things that we're building now will end up being as big an industry as the current computing industry. So if you add up all of the silicon that's ever been sold, and you add up all of the software that's ever been written to run on those things, I think that's about the same size as the eventual market for the descendants of this type of processor. And by descendants of this type of processor, there are several. People focus on the quantum mechanical aspect of what our chips do, but that's really a small part of the whole story. The chips are built out of superconductors, and I think a bigger part of the story, which is often not fully appreciated, is that building processors out of superconducting metals is a huge set of advantages. And regardless of whether or not they're using quantum mechanics, you can do things with these types of systems that you simply couldn't otherwise do in terms of power consumption and speed. And the complexity of the integrated circuit that you can put on may not be as big as in CMOS, but the punch you get for the devices that you lay down can be considerably greater. And so it's our hope that all superconducting processors in the future will be D-Wave products, and that these types of processors will service an enormous unmet need right now.
Let me throw in a question from the audience real quick here. Matt Swain asks a couple questions, but the second one is, any chance of the company going public on the radar anytime soon?
Well, all of the focus of the team right now is on the execution against an operating model, which increases the revenues of the company and moves us towards profitability. So things like public offerings are a means to an end. A lot of people think about IPOs or acquisition things as end points in a process, but for me, the only reason to ever do a public offering is to raise money. So if you can demonstrate that you have a significant need for a large amount of capital in order to move to the next generation or do something that was capital intensive, and it was the best strategy for accessing that capital, then we'd consider it. But in order to do that, your business needs to be built on a strong foundation of growth and revenue and profitability and margins. And the intent of the business as it stands now is to become a standalone business that is self-financing, that we finance the R&D through the profits that we make from the sale of the products that we make. Now, whether or not the public offering is in the future is really more about the management of cash than it is about any other aspect of the thing. And to a certain extent, it's not really something that I think about much. My concern as the CTO of this organization is ensuring that every time we release a new product, it's so much better than the one before that it looks like something completely different. And we've been doing that for a long time now. And I want to keep sure that every time we release a new thing, it's fundamentally qualitatively different than the one that preceded it. That's what I'm focused on.
Mm-hmm. Let me put you in the spot here and ask you this question. Tell us what is a quantum computer in 2 or 3 minutes at most.
Just 3 words. Well, there's a very simple and quick answer to this question. It's a computer that uses quantum mechanics in the course of running an algorithm. So it just to unroll that a bit. So an algorithm is a prescription for a series of steps that you will take to attack a problem. So for example, if the problem is to turn on your computer, there's a series of steps that you can do to make that happen. If you want to turn on 5 computers, it's a little bit of a varied algorithm. You have to go to the first one and turn it on and the second one. So algorithms are, baked into everything we do. In computer science context, they're a more formalized thing where you take a series of usually very non-trivial steps to solve your problem. The big difference between the classical and quantum computer is that when you are designing the prescription for solving a problem, in the classical world, you can't do anything that violates the laws of classical physics, which may be obvious, but it's fundamentally the cause of the difference between the two types of approach. And the reason for that is that the processor that you're running was designed specifically to be like a little clockwork universe. What goes on inside that thing is deterministic by design. That is, when you take an operation, there's a lot of attention paid to that operation always giving you the same answer.
Pretty much hardcore Newtonian in nature.
It is, but it's hardcore Newtonian by design. The fundamental difference between a quantum computer and a classical computer is that the quantum computer algorithm designer, the person who's designing the prescriptions for solving these problems or a problem, has access to operations that are prohibited by classical physics. So they literally violate the laws of classical physics. And they do so in a way that's fundamental. It's not just one line of prescription says do X, where X, you can do quantumly or not classically. It's that the entire architecture of how you write algorithms is vastly modified. And in some cases, it's modified in a way that makes the prescription that you're solving not even look like a conventional algorithm. So, for example, for the types of computers we build, there's no sense of a clock or gates, whereas the traditional way that you think about compiling a high-level language down to machine code, fundamentally at the bottom, what you're doing is you're compiling something to a bunch of gates. It's one way of thinking about it, that operate on clock steps. Mm-hmm. As in our case, we have no clock, there are no gate steps, and the algorithms are what are called continuous time algorithms. They operate without the discretization of time. And so you have to think about things in a totally different way, but the fundamental underpinnings of the whole distinction between classical and quantum computer has to do with algorithms. It's about problem-solving prescription. And when you add quantum mechanics, the algorithms become fundamentally more powerful. Mm-hmm. You can where you're going with less steps.
Mm-hmm. I see. Now, another question from the audience, this time from Maurizio Bisoni, who says, please ask Geordie about what kind of algorithm can be and cannot be solved with a quantum computer, because I always find this difficult to understand. He's talking about the difference between the classical and the quantum. In other words, the advantage that we gain from moving from the old model to the quantum model.
Okay. Well, those are two different questions. So the first one, what algorithms can you run on a quantum computer? Mm-hmm. Run all classical algorithms, because the classical stuff is a subset of the quantum stuff. Mm-hmm. But you can run others as well. There are known algorithms for using quantum mechanics, but there's the almost certain likelihood that that's only the tip of the iceberg as to what you could actually do if you had one of these things. And so we have some representative examples, kinds of proof of concepts of things that you can do more efficiently using quantum mechanics, quantum computers than you could otherwise. such as famous examples like Shor's algorithm for factoring products of prime numbers and Grover search, which is a kind of an artificially constructed proof of concept for doing a type of search. And of course, the most interesting of all of them, the adiabatic algorithms or the quantum annealing algorithms that solve optimization problems. And the reason I say those are the most interesting is that optimization problems are everywhere, whereas factoring products of prime numbers is a problem that only has one application as far as I know. Mm-hmm. It's codes. And that's not something that a company like us is all that interested in. In fact, we're not interested in it at all. It's not a commercial business. Mm-hmm. The Grover search is an artificially constructed algorithm for an artificial problem that doesn't appear anywhere in the real world. Mm-hmm. So the adiabatic algorithms are ones that attack real world problems with a quantum algorithm, and those are the ones that we're focused on. But I think that once quantum computers start to become more commonly available and the tools to program them mature, you're going to get an explosion of use cases of optimization and possibly new quantum algorithms coming out. The guys at MIT, for example, have been thinking a lot about using the theoretical computer science version of a quantum computer, which is called the gate model quantum computer, which, by the way, will probably never be built, but they're a nice theoretical model, and using them to construct machine learning algorithms for that type of computer. So there's progress in this idea of what you would do with one if you had one, which is the quantum algorithm side. But you can do anything you can do with a classical computer, and more.
Mm-hmm. Another question here by the audience, David Dalrymple, one of the Singularity University GSP students there before me, I think. He asks, what is the greatest limiting factor on the development of quantum computing into a commodity technology?
So that's a very good question. I think the tactical answer, what actually bottlenecks our progress now, is fabrication technology, and I think that's true for all quantum computing designs. This is something that I think it's going to become obvious in hindsight, but I think it's not so obvious to people today. Is that bottlenecks to building quantum computers have nothing to do with physics or computer science. They have to do with engineering. And if you're going to build a VLSI processor, which is what you need to do to build any kind of quantum computer, you need to be able to build it. It's pretty obvious, right? And the trick is that all reasonable quantum computing designs that have ever been proposed use different kinds of materials and devices in their operation. And the ability to fabricate those things at the scale that you can fabricate current semiconductor chips doesn't exist. And this is something that is ignored almost exclusively by people who talk about quantum computing, and it baffles me because it's the only thing that really matters. If you can build any design you can think of fast and get it back just like you thought you wanted, you can do rapid, high-throughput experimentation to try to weed out bad ideas and focus on good ones. Mm-hmm. The ability to build large-scale processors using a novel material set and device set is a staggeringly difficult problem. In the semiconductor world, literally trillions of dollars with a T have been spent on building modern fab, and dozens of years. A staggering investment in what is obviously the most difficult and wonderful manufacturing process that has ever existed in the history of humanity. And if you want to build a commodity quantum computer processor, you need to be able to fabricate things the way that Intel uses TSMC to fabricate things. And in order to get there, you need to spend hundreds of millions or billions of dollars developing that technology as a precursor to even having a chance. So if any of you budding entrepreneurs out there want to try to build it, here's my advice. Focus on being able to actually build things quick and easy and cheap. And if you think about how you're actually going to construct your technology, what you will quickly find is that there is nowhere you can go in the world to get the things you want built. And you're going to have to do it yourself. So how are you going to do that? I often hear mostly academic scientists, but also just pundits saying, well, you know, if I wanted to, I could build a 100-qubit quantum computer in a few months, but I just don't because I don't see the point. That is utter, can I say bullshit?
Sure, you can say anything you want.
The fact that you can build 1 or 2 qubits means absolutely nothing, because when you go from 1 or 2 to 100 or 200, the number of problems you need to solve in terms of actually fundamentally being able to build the thing in a way that works, they grow in by leaps and bounds, orders of magnitude. So the number one biggest problem in building a commodity technology using quantum computers is the inavailability of fab. And so a lot of the work that we do and a lot of the advances that we've had are fundamentally about that. How do you build chips to be able to embody enough complexity to get them to do something interesting in a way that is modeled on the semiconductor industry?
Mm-hmm. So what can you tell us perhaps about the ways that you have resolved some of those huge obstacles in your own building of your own computers?
Well, there's a few things that are lessons that I think that we've learned that you absolutely need to follow. I think that the way we did is obviously not the only way, but here's some guidelines to be able to tackle a big problem. So first, my buddy Eric, who actually runs the fabrication stuff, has a saying that he always says, you have to respect the problem. And this is a very important idea. So when you're talking about doing something new, often people vastly underestimate how hard it is. You know, just doing something simple can end up being a lot of work. When you're trying to do something complex that has a lot of moving parts, it's going to be a lot harder than you think. So in order to successfully tackle any difficult engineering problem, the first thing you need to do is respect the problem. It's going to be a lot harder than you think. And so that's one. Second thing is you need to have the world's best people working on it. If you can't do that, you failed as a leader. So the one thing that I think I've been very successful at personally in this enterprise is locating and seducing to the company talent that would otherwise not have come here by painting a picture about how great it's going to be to be involved in this project. And often people who are very good, they're kind of like bored with the glass ceilings that they have in the organizations they're in or in the culture that they're in. They want to try something bigger, be involved in something bigger than that. So you need to get those people. If you're going to try to do something, you can't have a bunch of people who are like B-level people. They all need to be A+. If you have somebody on your team that's not an A+, they shouldn't be there. So that's rule number 2. Rule number 3 is money. And it's corollary time, because they're the same thing, and there's a conversion factor between time and money off. In order to do something big, you need to fund it properly. And this is another thing that people don't get, that if you put in a half the money you need, you're not going to get a half the output. You're going to get nothing. If you put in 9/10 you need, you will get nothing. Of the money you need in order to get something at all. And that number is often daunting. So if we go back to the lack of the Bell Labs and Xerox PARCs of the world nowadays, these types of projects that we're talking about, you can't even begin to attempt them without, say, $100 million. It's the price of the entry fee to even try. If you don't have that much capital and the wherewithal to manage it and invest it wisely and efficiently, don't even try to tell me you're trying to do this, because it's ludicrous. Anybody who's ever built anything of note in the world knows, I mean, I'm talking about hardware here, just entirely. If you're going to build a new chip, You can ask Intel, how much does it cost you to build the next generation of chip? And I think that the number you get back would surprise a lot of people. It's damn expensive. And the reason is you're going to build a physical artifact, a new car, an electric car, a new space launch vehicle like SpaceX is doing. Anything that has to do with the creation of a new physical hardware artifact.
Tesla car, for example.
You're talking about an investment that's just not a lot of money. For in some ways of thinking about it. But on the other hand, $100 million sounds like a lot, but look at the profit of, say, a big oil company every year, and then figure out how many hundred millions of dollars fit inside that budget. How much money is spent overseas in military efforts by the United States. That number is big. It's much bigger than 100 million. So I think those are the three things that I would say are absolutely essential to doing a big project. You need to respect the problem. You need to get the very best people in the world, and you need to fund it adequately and allow for enough time for it to mature into what it needs to be.
Yeah, I've been happy to interview Intel's chief futurist, Brian David Johnson, on this show before, and he said a lot of things in keeping or in support of what you just said too, in terms of the investment and stuff like that. Now, let me ask you a little bit more about the sort of the specifics of the models that, or the latest model that you can perhaps talk to us a little bit more about its capabilities. It was a big jump from the previous version of your machine, and what it took to get that sort of breakthrough step to get you there to that next level, and then eventually engage people such as Google and NASA who got interested in purchasing one.
Well, the relationship with both NASA and Google has been ongoing for a long time. In fact, my friendship and working relationship with the Google guys goes back 6 or 7 years, and over that period of time, we've done an enormous amount together. I think this goes back to this persistence thing. I have been attempting to convince a variety of folks, not just Google, but many, that the future of their business may depend on having access to this type of technology. And I can go into why I think that a little bit later if you'd like. And that process of building the relationships and credibility and to enter into such a deep partnership is a time-consuming endeavor. It goes back to respecting the problem. If you want to engage with a group of people like them who are arguably the best in the world at what they do, I'm specifically talking about machine learning now. They're clearly the best at what they do in several other dimensions, but in terms of machine learning, I think that there are lots of other strong groups, but they're among the best. You need to be absolutely sure that the story that you're telling holds together, because they're going to try to rip it to shreds in every different way that they can. So when we brought this story up to those folks many years ago, they raised some obviously good questions about whether or not the story held. And a lot of those things had to do with things we couldn't answer without building faster and better machines. So over the years, we've worked together on algorithmic things, how you would use the machine if we could build one sufficiently big. And as the progression of the technology went onwards, they reached a point where the technology matured to the point that they thought that it was ready to actually run on the problems that they cared about, and that's the genesis of the current deal. And like Google, with NASA, we worked with NASA or its cousins, such as JPL, for a long time, even longer than Google. And we have a long history with those guys of being world-class, always doing things better than everyone else that was around them. And it built a certain trust that we could deliver on the future of this technology, and therefore they wanted to be involved as well.
So I read this article on Wikipedia, so I don't know how accurate it is, about the Vesuvius system, which is supposedly the one that Google and NASA bought. Can you tell us a little bit more about about it. It says it has 512 qubit. How should I say it? Processors. Is that a proper way of saying it?
Yep.
And so, can you tell us a little bit about that machine and so on?
Sure. So the first machine we sold was the predecessor to this one, which was very similar in many respects. It had a big black box inside of which was a machine called a dilution refrigerator, which is a machine you can buy from several companies that cools a payload down to about 10 millikelvin, which is very cold. And inside that refrigeration environment was a bunch of custom stuff that we built that allows you to get signals in and out from a chip, which is wire bonded at the base, which is the brains of the computer. So the initial machine that we sold had a certain type of wiring and a chip that had 128 qubits, which was codenamed Rainier. And that was installed at USC, and is the subject of many of the papers that have been coming out recently as the final, the publication of a lot of the work that was done on that machine. Mm-hmm. That machine has subsequently been upgraded to the recent technology, and the main upgrade is the processor itself now contains 512 qubits, mm-hmm. But that's not the only difference. It also contains a hugely sped up input-output system, so it's a lot faster to use. And the qubits themselves have been modified significantly to, without getting into too much detail, be more quantum. So there's a way to do this with superconductors, and it basically boils down to making them shorter. They're loops of metal. If you make the loops shorter for a variety of reasons, they get better in quantumness. Mm-hmm. So we installed that particular chip, which is codenamed Vesuvius, which is the 512 variant, mm-hmm. Both USC and at the NASA Google site. And both of those machines are now fully operational and solving problems for the customers.
Mm-hmm. Can you describe, are you allowed to tell us a little bit more about the kinds of problems that they are trying to resolve with your machine?
Sure. So the one at USC is primarily used to basic research. So that has a variety of different threads to it, but things like what are the characterizing the error sources in the thing. So if you try to run a problem and you don't get the answer you want, why, what's happening? Are there ways to remove those errors? The problem questions like, is there entanglement present? And if so, how do you measure it? And if so, how much of there is there? If so, how does it affect the computation itself? Questions like, what's the computational scaling of a variety of different approaches to solving problems? So if you increase the size of the problem, how much harder does it get for the computer to solve it? Mm-hmm. So that's the USC machine is primarily used for that purpose. The one at the Quantum Artificial Intelligence Lab is mostly about figuring out how to best use the chips to run machine learning algorithms of a variety of types. Mm-hmm. But ultimately, the machine learning aspect of it is a subset of a bigger issue, which is how do you give human level cognition to machines. So learning is a part of that, maybe a very important part, but mm-hmm. it's only a part. Mm-hmm. So the research that's going on there, I'd still characterize it as basic research, is how do you connect the fundamental capability of the machine to machine learning and thereby improve the performance of machine learning algorithms that are run on this type of hardware. Mm-hmm.
I would come back a little bit later to the issues related to machine learning and consequently artificial intelligence. But before that, I want to ask you, which is also a derivative of another audience question by Peter Rothman. Is there a version or what's your version of Moore's law, and how do you see that develop into the future, say in the next 5 or 10 years?
So one of our investors, Steve Jurvetson, coined this Rose's law, which I don't know. I have mixed feelings about it. It's nice to have something named after you, but it feels a little bit like self-glossing. Like if you give yourself a nickname, it's not okay. So the underlying.
But let me interrupt you here for a second. Gordon Moore didn't name Moore's Law, right? It was named after him, and it seems to me that you didn't name it Rose's.
I kind of objected to it strenuously at the time. People are, I suppose some people anyway, are using. So what it's supposed to characterize is that at D-Wave anyway, the number of qubits we've been able to marshal to perform computations has doubled every 12 months for the past 9 years. So the same type of exponential scaling of the integration of the physical hardware when you count by qubits, which may actually not be the right metric, but if you do, you find this steady doubling every year, and it's progressed at this rate for 9 years now. So when Moore's Law was first coined, I believe they only had 5 data points. We have 9.
I think they had 3 actually.
Okay, it was some smaller number.
Yeah.
We have more than that now, so I think it's legitimate to make a projection that going forward into the future, the number of physical qubits on the chip will continue to double every year for the next 30 or 40 years.
Mm-hmm. Very interesting. Another audience question here, and this one is kind of anonymous. How do you resolve the interference decoherence problem?
Yeah, so that's a good question, and here's a simple-ish answer. So when you operate a quantum computer, you have several different options for how you do so. The model that's dominated the discourse over the last, say, 20 years or so is this so-called gate model of quantum computing. And in the gate model, the assumption is that you have access to all of the states of a physical system, and they're all equal in some respect. One of them is not any different than another. So if I wanted to set up, 111 as a bit string, that isn't fundamentally different than 000. They're both just different types of the same thing. Mm-hmm. But in quantum mechanics, what those states represent, you can think of as energy levels. So imagine you have a hydrogen atom, because you may remember, a lot of your listeners may have studied this in school or be familiar with the idea. In a hydrogen atom, you have an electron, which is somehow distributed around the nucleus. And all things being equal, it likes to be in its ground state, which is sort of spherically symmetric about the nucleus. If you add energy to the system, the electron can hop up to excited energy states that are quantized. So as you go up in energy, they make jumps in energy. Now, in the gate model, those different energy levels correspond to these different bit states. And what you have to be able is to create superpositions of all of these energy levels and maintain them over a period of time that's fairly long. Now, the assumption that's made there is that nature doesn't care so much if it's up here or down here, but that's not true. Nature cares a lot, and the reason is thermodynamics, ultimately, that systems in contact with other systems want to equilibrate to them, and any physical object you've got is surrounded by an environment, a bath, that's at a certain temperature. And what will happen is that central thing will want to become like the temperature of that thing, and ultimately what that means is it will try to decay in energy. Mm-hmm. So something up here wants to decay. It's the reason why lasers work, and basically anything that emits light is using this principle of decay of some underlying thing down to an emitting photon as it does so. So in that model, decoherence manifests itself by, among other things, this propensity for the system to want to decay out of the states that you're trying to use for the computation. So if I say I want a superposition of 111 and 000, and then I want to perform an operation on that superposition, if 111 becomes 000 somewhere in that process, what you get is jumbled garbage out of the end. The thing is not robust against that kind of error. And so there was a dogma that was built up in quantum computation that this decoherence thing always kills you no matter what. And you absolutely had to do things under this particular time or else everything would fall apart. But that's a very silly perspective in hindsight, because there's not only one way to build a quantum computer. So the way that we do it, these different energy levels still exist, but the computation only resides in the lowest one. And what that means is that that lowest one is robust in the sense that it can't decay. There's nowhere for it to go. It's the ground state of the system. It's just like putting a hydrogen atom in its ground state. If you don't do something to it, if you don't add energy to the system, it will remain there forever, for all eternity.
Mm-hmm.
And I think that the point of confusion that people have is that they think that that ground state is somehow a classical thing, that the ground state is subject to decoherence in the same way that one of these excited states would be, but it's not. So the ground state can contain massively entangled state. So you can take all of your qubits, entangle them to the maximal amount that they can be, and that entangled state can be the ground state of a properly constructed physical system. And when that's the case, there is no decoherence time. It's not the right measure. You can let it sit maximally entangled for hundreds of years, and it will never, ever, ever change, because it can't. There's nothing for it to decay into that's better than that. Mm-hmm. It's protection against the type of error that people usually talk about with decoherence completely changes the theoretical analysis of the system. There are analogs to the type of errors that are induced by the decoherence time in the adiabatic model, but time is no longer the important scale. It's actually the dual of time, which is energy. There's a whole other field of art that dealing with how do you characterize the transition to classical behavior from quantum mechanical behavior in this type of system. And it's a little frustrating when this thing keeps coming up, but I kind of understand it because a lot of people keep repeating this, but it's simply false. There is no such thing as a time scale for decoherence that matters in the adiabatic model. What matters instead is something which is sort of the dual of time. It's the broadening of the energy eigenstates, the energy levels due to the interaction with the environment that matters. Mm-hmm, mm-hmm. Different parameter that you can also characterize and measure. And in our case, it's very small. A related thing that I often hear is that D-Wave makes noisy qubits. That's total bullshit. The qubits that we make are known to be among the quietest superconducting qubits that have ever been constructed. And the fact that they're within this matrix of literally hundreds of thousands of other devices that are all doing things in the service of doing computation is rather remarkable, and it goes to the strengths of using superconductors for the hardware substrate for quantum computers.
Mm-hmm. Now, you said that there's more than one way of building a quantum computer. Can you tell us a little bit more about the sort of traditional von Neumann architecture and the issues that you sort of discovered along the process of trying to build a quantum computer, and then how you eventually were able to move beyond that kind of traditional von Neumann architecture, which is used for pretty much every classical computer out there?
Yeah. So even in classical computer hardware, there are an enormous number of different ways that you could build a universal classical computer. So, for example, you could build one out of neural nets, like hardware-based neural nets. And in fact, there's a very interesting project that IBM is pursuing that has that as its objective. And
Synapse?
It's fascinating. Yeah, that's right. And it's not the only one. There are also projects that have been initiated and have sometimes been very successful to build probabilistic hardware. That is hardware that by its nature attempts to introduce randomness into computations that is not the same as the way that conventional computers are architected. And then there's the obvious things like FPGAs and their related cousins, ASICs, application-specific integrated circuits. So even in conventional computing, there's a lot of different ways that you can go about trying to do what you want to do. And ultimately, if you want to have superior performance on some type of specific problem, you'll always get a bump by doing something very specifically designed to model the problem or to embed the algorithm that you care about into the hardware instead of doing something general purpose. So even the conventional world, there's lots of different approaches. In the history of the conventional computing development, the von Neumann style architecture emerged as being the clear, correct path forward to build general purpose microprocessors. And it was obviously the right choice, and it's been proven to be so over many years of continued improvement. And now that I would argue that microprocessors as they currently stand are the most advanced technology that we've ever built. I don't think that there's any doubt about that. The fact that you can get billions of nanoscale all to work together and virtually never ever give you an error when your grandma is running on the cloud to do the amount of complexity that these things hide is staggering. So it was a really good choice, and it was the right one. Mm-hmm. In quantum computing, the story's not. So in the early days of thinking about how to build a quantum computer, one of the clear things that you could try to do is take all of that wonderful architecture that worked so great and just make everything quantum. So to a certain extent, the gate model of quantum computing is just that. You take the way that computers work now and you make everything quantum. So you still have high-level language. You still have a compilation process that generates gates. You apply those gates in some physical medium that has physical gates in it. And the thing cranks along every time step. You perform a series of gates. And then at the end of the series of gates, you get the answer that you want. And using quantum mechanical gates allows you to perform hard computations with many time, like some kind of scaling advantage on how many gates you need. So, for example, if you needed 2 to the n gates to do something classically, maybe you only need 2 to the n over 2 gates to do quantum training, which is a huge difference. So that's the gate model. Now, just like in conventional computing, when you have a lot of freedom to choose the architecture, in quantum computing, it's the exact same story. You have the freedom to choose from a large number of possible different architectures for your processor. And unlike in conventional computing, the von Neumann style gate model is not the right way to build quantum computers for a variety of interconnected reasons. So one of them is this issue about the decoherence time. But that's only one of them. You can go through a long list of reasons why the gate model is likely not going to ever happen. It's not that it's physically impossible to build one. I buy that it is. But, it's physically possible to build a ladder to the moon. Mm-hmm. There are no laws of physics that prevent us, as far as I know, as long as you have the right materials and enough time and energy and money, that you could actually build like a step ladder that went all the way from the Earth to the moon to get there.
It's like building a space elevator that ends in the moon, basically.
No, because I think a space elevator makes a lot more sense than a ladder.
But the elevator is like an advanced version of a ladder in a way.
Yes. So would you rather have a space elevator or a ladder you had to climb? I guess the point I'm making is that if your objective is to go to the moon, there are lots of different ways to do so. Mm-hmm. And the claim building a ladder to the moon solves the problem and is physically possible to do is probably true, but it's obviously not the solution.
Yeah, I agree. Yes, so absolutely.
In quantum computers, the gate model is like a ladder to the moon. Mm-hmm. It's physically possible, and it probably would get you where you wanted to go ultimately, but mm-hmm. there's absolutely no reason to pursue that path now that with all of the knowledge that we've obtained. And it's almost ludicrous to even hold to that belief anymore, given what's known now about quantum mechanics and the complexity of engineering real physical devices that subtend that kind of idea, where these other ideas, and ours is not the only one by any means, there are many cousins of this approach that we've taken that are so much more sensible than that it boggles my mind that smart people haven't kind of realized yet that is just simply not an interesting path at all for technology. Now, for science and that we were talking about earlier, the interest in understanding, the ontological nature of reality and what's physically computable in the universe, that's a different story, because the gate model is a beautiful model for the development of the theory of the power of quantum computation. So things like theoretical complexity theory, which are virtually disjoint from reality in the engineering world. It doesn't matter at all. It's not even relevant for the development of algorithms, or if it is, it's marginally relevant. Mm-hmm. That kind of thing, I think, is much better to use something like the gate model, because it's a lot easier to manipulate symbols on paper in that model than it is in, say, what we do, which is a lot more difficult to theoretically analyze, even though it's a sensible thing to try to build. Other than not, those other things aren't.
Mm-hmm. I see. Now, one of the things that I remember, for the audience, I should say that I had the pleasure of meeting you in person during the IdeaCity conference in Toronto a couple of months ago. And one of the things that I remembered you saying during that conference was that a plane is not a faster horse. And so I want to ask you, how powerful is your latest model versus, say, the most powerful classical computers you can buy on the market right now? Because you did say that basically a quantum computer is able to do pretty much all of the computation that the classical one is able to do. So how do they compare on classical problems?
Well, I think that the honest answer to all of those questions is we don't know yet. The nature of this thing and what I was talking about earlier, they're difficult to theoretically analyze, means that often answering questions like this is a matter of empirical testing. You have to actually run the experiment to find out how well they perform. And that is an uncomfortable position for a lot of people who study computer science and physics, because often the theoretical analysis of something is an important part of the understanding of how it works. With this sort of machine, we're beyond the limits of where you can effectively theoretically analyze. It's too big and too quantum. So you're in this very interesting, mysterious no man's land between a quantum system that's small enough to actually figure out what it's doing from first principles and the classical world. And this is an area where there's going to be a lot of surprises. People who speak with certainty about how powerful these machines will be in the future are delusional. They're thinking about the problem in the wrong way. They're assuming that the understanding that we have from the quantum side, which is typically deals with small closed systems, will directly apply to something like this. And that is not necessarily true. And in fact, I think it's clearly not true. The ultimate power of a machine like this is not well understood. So the way that we're proceeding with all of our engagements is to define a set of tests that say, okay, given that we want to do this, how long is it taking this machine? And also a very important question, how much longer does it take when we make the problem bigger? This is this computational scaling of the thing. Mm-hmm. And can we analyze that particular case to see why that behavior is happening? Now, how powerful is it versus conventional classical things is a very difficult question to answer, because the answer depends very, very strongly on the specifics of the problem. There are problems that you can run that a conventional laptop can do 1,000 times faster than our thing. There are problems you can run that our thing is 1,000 times faster than the fastest processor that we know of. How you deal with this kind of difference is a new emerging field of science, because there's never been a machine like this ever in the history of humanity. Mm-hmm. There's been a machine like this. In some ways, I like to think about the machine at USC and at Google. Those machines are a little bit more like the LHC than they are like your laptop. Your laptop is a very well-characterized thing that is very easy to understand how it works now, because it's had 40 years of study about these sorts of things, and the people who design them so that you can study them well. Mm-hmm. and run things like linear algebra on them and know exactly what's going on. With this new thing, we're in totally uncharted territory. The actual performance of it, how it works, how fast it works, its ultimate limits are all completely unknown. And that's another very important point I want to get across to people, is that no matter what you hear about an experiment that was performed or the opinion of someone, the reality is that all experiments are for special cases, and you can't infer the general behavior of this thing from any one experiment.
Mm-hmm.
You could do another experiment where the result was absolutely 100%, 180 degree different.
Mm-hmm.
And the real answer is no one knows how powerful these things will be.
Mm-hmm.
Anything from they will be no more powerful than conventional computers in the sense of complexity. In terms of their speed and energy consumption, they're obviously better because they're built out of superconductors. This is the reason why people have been going on about superconducting stuff for a long time now, is that our thing is already orders of magnitude better than any other processor that's ever been built in power consumption and speed. Like this is what you can think of as the clock speed, even though it doesn't have a clock, the natural frequency of the devices.
Mm-hmm.
But even if it doesn't scale better than a conventional computer, that's kind of the worst case. But it still remains the possibility, and the theory guys don't like to hear this, that the scaling of these things is flat. In fact, the thing that's the most consistent with all of the experiments we've ever done is the time it takes to run a quantum annealing algorithm is not a function of the problem size. Now, is that actually true? We don't know yet, but it's certainly consistent with the data that we've gotten. If we act like real scientists and we trust the experimental data that's come out, that is still a consistent possibility with machines like this, that it actually doesn't take you any longer to run certain types of problems when they get bigger than if they're smaller, which would be shocking, and of course it would upend a lot of our beliefs about the way the universe works. But if we're just being data-driven and we forget about the theoretical arguments, it's still a possibility. So where will it all end up? No one knows. That's why we like to have partners like Lockheed Martin, NASA, and Google who are willing to enter into this multi-year exploration with us to try to find out the answers.
Mm-hmm. Yeah, I appreciate that answer very much, but I'm just wondering about the obstacles that you're facing with a sales pitch in a business setting, right? In business, most people are used to see things black and white, kind of, right? Profit, no profit, yes or no kind of thing. Do it or don't do it. So they're thinking, okay, I have $20 million to buy a new computer, and I can buy a classical supercomputer, which is going to give me such and such processing power, and I have the option of buying Vesuvius. Now, how do you make that call? How do you make that decision? You have to somewhat compare the two, I guess. How do you do the sales pitch for you? I just wonder, in a situation like that. Say I'm a total ignorant of physics and of quantum mechanics and of any issues. I'm just like the person who makes the decision, though. $20 million, two computers. One is yours, the other is a classical supercomputer. How do you convince me that yours is the better deal? Or better value for the money, or the better option?
So the way that it's worked in the past with all of the people who've engaged with us is that we've worked with all of them for a long time before they committed any dollars at all. So one of the answers to these things is that nobody who first sees this for the first time, we'd expect to enter into a relationship like this. The way that we build relationships with people is that we work with them for years, in some cases many years, and build the trust that the organization is stable, it's progressing and maturing predictably, that the types of performance that we're seeing is continuing to grow. And then the ultimate decision that's made is putting aside the question of which of them gives me better return on my investment in the short term. Let's put that aside. So I have $20 million, and I wanted to invest it either in a new technology or an existing technology. So on the side of the existing technology, you know exactly what you're getting. So you can plan out all of the stuff that you need to know with very little uncertainty. and you can calculate the return on your investment very easily. With a new technology like this, you have a bunch of unknowns. So one is, will it actually be performant versus that other $20 million? We don't know. But there's an argument to be made that if you look at the historical trend, which now dates back 9 years, the types of problem that this thing solves, it's getting a lot faster on them in remarkably short time. And it doesn't take very long on this trajectory to make a very compelling argument that there is no reason you'd ever run one of these problems on any machine other than ours in a few years. So it might not be this generation, it might not be the next generation, but maybe the next generation after that, you're going to get to the point where if you want to compete in your industry and you rely on this type of computation, you cannot ignore this, because if you do, you will cease to exist as a business. And the point of pain for the people that we're dealing with, that this machine potentially alleviates or gives them an advantage on, is a business making, it's like an industry making or breaking thing that we're talking about. So with Lockheed Martin, it's validation and verification of complex engineering systems. With NASA and Google, it's big data and machine learning. Mm-hmm. Those organizations can't afford to fall behind in these things. So if a new technology arises that has a chance of completely upending the apple cart, mm-hmm. the decision that has to be made by the non-technical person is, where is the risk, can I quantify it, of losing my position as a leader in this industry? Mm-hmm. Lockheed Martin, what if a different company, one of its competitors, got access to the ability to build machines at 10 times the scale that Lockheed could with a tenth the bugs or a tenth the cost? What happens to them? They could die.
Yes.
So the same goes for the NASA and Google, is that the problems that they're facing are daunting ones that the current technology is simply not on a trajectory to solve effectively. Mm-hmm. And so looking for other options, and the investment in a partnership with us has lots of corollary benefits. One is, I keep talking about the A+ people. The people within this organization are a concentration of some of the world's best talent in several fields. Some of the best computer scientists, physicists, and engineers, technicians, business people in the entire world are concentrated in this one spot. And so that you get not only the actual physical hardware, you get to participate in this wonderful, mysterious journey as we go forward. And that is just from a human perspective, just a marvelous thing to be able to do. So not only is there the kind of tangible risk-reward calculation that has to go on, there's also this business that humans like to be involved in big exploration. And this is about as big an exploration as you can get. It's the most interesting physics experiments that's underway in the world today. It's more interesting than things like the Higgs boson and the LHC, because it matters a lot more to the 7 billion people on this planet. If this thing works the way that it does, it will impact the life of virtually everyone on this planet, unlike something like, where are the fundamental particles and what are they made out of? Mm-hmm. This thing has immediate, tangible impact on a lot more people than that.
Mm-hmm. I see. Now, just for clarification for our audience, when you say LHC, you mean the Large Hadron Collider, right?
Right.
Yeah, that's okay. And now, you keep saying there's no clock that you're using, but I watched this video with Eric Ladzinski, and he was describing how he came up originally with the idea about the first qubit. And he basically said, if I remember, it's a metal circle in which you run, basically imagine like a velodrome, he says, in which you race both clockwise and counterclockwise on your bicycle at once, all at the same time. Yeah. So this was for him the idea of the first qubit. Mm-hmm. And now, I don't know how that carried through and whether that metaphor still holds, but tell us a little bit more about if this is not a clock in its own right, or why is it not a clock in its own right, and then whether when you're talking about 512 qubits, you're talking about 512 of these sort of devices in your latest chip.
Yeah, so the analogy is a good one, I think, and Eric was responsible for the selection of the type of qubit that we started working with in this project. And I can tell you that even though in hindsight it was obviously the right choice, back then there were lots of different things to choose from. So Eric's insights were vitally important to getting us on this sort of Rose's law track. So maybe we should be calling it Ladizinski's law. So the qubits are they're called SQUIDs, which is an acronym, superconducting quantum interference device, and physically they're loops of superconducting metal. And the neat thing about these loops is that the currents that flow in them are quantized. So you can only have a certain amount of current flowing in one way or the other. Just like you can only have, in your hydrogen atom, you can only have certain allowed energy levels in the system. You can only have certain allowed currents. So these currents, you can set them up so that the two different current states, say clockwise and counterclockwise around this loop, the device can be configured such that they have the exact same energy. And that, when you do that, the system loses the ability to distinguish between the two, which you can think of as putting in a superposition of the two states. So the device subtends both of them simultaneously. And so if you perform an operation on that device, you can sort of get two for the price of one in some sense. It's not that simple, but that's kind of the basic idea. Mm-hmm. And the currents have magnitudes of about a microamp. So they're not tiny currents. You're talking about large numbers of charge carriers flowing at the same time. So your velodrome example, if you think of a bike rider as being one electron, or say one Cooper pair, which is a paired bunch of electrons, the charge carriers and superconductors, there's something like 10 to the 17 of these going one way and the other way simultaneously. So it's more than just one.
Wow.
But the thing about that device is that it was the very first device where macroscopic quantum effects were ever seen. So this was done in the early 80s. And it was a question back then, not so long ago, whether quantum mechanics could ever exhibit itself at the level of the macro scale in this way. And that was the first experiment that settled that. The answer was yes. And here they are. Here's the currents. And look, they're flowing in both directions at the same time. So that was a breakthrough experiment. And one of the guys who was involved in that got the Nobel Prize for something else, but it was a big deal. And that device now has gone through multiple evolutionary changes to where it is today, but it's still fundamentally the same idea. It's a loop of metal with current flowing in it, where the bit states are clockwise and counterclockwise. And you can manipulate the device to do all sorts of wonderful things, but fundamentally that's how information is stored. And yes, in Vesuvius there's 512 of those loops. There's a bunch of other stuff too that's also important, but the processor does contain that number of squids.
Mm-hmm. So, Geordie, I have only a couple more questions here on quantum computers, and then I want to move on and talk a little bit more about artificial intelligence and so on. But here's another question from the audience by Roman Saiklu. Please ask Geordie why there are so many quantum scientists who are skeptical about D-wave computers. And let me just add some of my own personal impressions here. I've met a lot of people from the Perimeter Institute here in Ontario and a few others, and I'm always very surprised myself to see how absolutely skeptical they are about the D-wave quantum computer. Many of them tell me, they have no peer review. Their Moore's law is total nonsense because it hasn't been confirmed and it's only about comparable to what their previous stuff was, and we have no ways of confirming or denying it. Like all kinds of criticism. Basically, one of them I think told me something like, well, maybe they made some kind of a computer working at a very cold, in a very cold environment, but it's more like a classical computer and it's not it definitely is not a quantum computer. I mean, I'm not a quantum mechanics physicist or anything like that, but I've been kind of really surprised by the amount of skepticism that I've met. What do you want to say about that? Why is that the case? Am I wrong to say there's so much of it?
Well, no. I think there is quite a bit. As to why there is, I can hazard a few guesses, but ultimately, I'm not sure. And I think that when you do something completely new and it's unexpected, there's a general human propensity to question it. So there's just a question of basic human psychology that when presented by something that was unexpected, you wonder whether it's real or not. I think that's a natural reaction. But there's a lot of other things going on here. I think that the very clear and consistent message that we've provided to the academic community about the gate model being the wrong way to go was not accepted in the spirit in which it was offered. I think people view the emergence of this new type of model, forget about D-Wave for a second, just the emergence of a new type of computational model, which is clearly better in many important respects. Hard to argue against that now. That was viewed as being a threat. So if I built my career trying to build a certain kind of machine or understand a certain kind of machine, and it's becoming maybe pretty clear that that thing is not going to ever come about, what happens to my funding, for example? What happens to my professional reputation as a scientist? So a lot of people who study this field are very concerned that if what we say is true, it has negative impacts on them personally and their efforts. Now that is a total misreading of what's going on here. And if any of you are watching now, you know who you are.
It's possible. Let me tell you, it is possible because I have a few of them.
Yeah, sure. The emergence of a real functional quantum computing technology does nothing but increase the funding, the visibility, and the opportunities for people who work in this field. That is so clearly true that I don't think I need to elaborate. Think about the field that I was originally in, which is high temperature superconductivity. Where are all the people studying it now? They're doing other things. Why? I'll tell you why. It's because we couldn't build anything useful out of it. That's the fundamental reason. If we'd been able to find a way to use those materials to economic effect, there would be a thriving industry of people studying those materials now, and now there isn't. It died. Quantum computing is the same thing. If you want to have a thriving, vibrant ecosystem of basic research investigating all of these things, you absolutely need to have it matter. And the only way that these things matter is if people can use them to do something useful. And so if you have an effort like ours, whose stated intent is to build something that actually does something useful using quantum mechanics, it does nothing but good for the field as a whole. Mm-hmm. I think that there's also, we're not the first, and we won't be the last organization to face this type of psychology. The one that I would use as a very recent historical analog is Craig Venter and the Human Genome Project in Celera. Mm-hmm. There are a lot of analogies between D-Wave and Celera. In both cases, we presented a shortcut approach to attacking the same fundamental problem in a very different way that required a tenth the amount of money and directly, I gotta say threatened, but challenged the existing dogma of the world scientific community and then demonstrated that they were right. So in the case of sequencing the human genome, it's a lot easier to just print out all the ACTs and Gs to demonstrate that you've succeeded. With building a quantum computer, it's a little bit more difficult than that because demonstrating a model of computation is not a straightforward thing. You can't write it down in a bunch of ACTs and Gs. But we're at the point now where we've completed the sequencing of our own human genome in this project. These machines are absolutely 100% without equivocation quantum computers. The statement about lack of peer review is just absolutely laughable. We have more peer-reviewed articles in journals like Nature, Science, and Physical Review Letters than any other startup that you can find. Go find me a startup that has more publications in those three journals than us, and I will eat my hat. We have, at last count, something like 70 peer-reviewed articles on all aspects of this technology. It's so well documented in terms of how it was constructed and what it does and how quantum it is and how the model works and all that, that if you had $100 million, 10 years, and a team of A-plus people, you could reproduce what we've done yourself just by reading the paper. So I encourage you, if you believe that there is no peer review of what we've done, to go to our website and look at the content there. And also the quality of the people who've been co-publishing with us. That's just simply false. It's silly. And hopefully it will eventually vanish. You know, a lot of this stuff, the stuff in the blogosphere and some of the rather strong personalities who've come out to voice their displeasure at our the nature of what we're doing and how we're attempting to do it. It's just noise. It's just this transient stuff that will go away in time. And even if this project never progressed another step, even if the only thing we ever did was build what we've done, this is one of the most remarkable accomplishments ever in the history of human technology development. How far we've gotten with the limited budget and people that we've got, the amount of obstacles that we've challenged and overcome, I don't think it has any peer. No matter what kind of industry you can think of, it's very difficult to think of an industry or a company that has overcome the kinds of problems that we've had to overcome, created a real artifact that's now being acquired and bought and used by some of the best, biggest companies in the world. There's just a very few, if any, historical.
Yeah, my response to, in one of those occasions, I was discussing it with one person from the Parameter Institute, and my response was like, well, Google and NASA are very hardcore scientists. I mean, wouldn't they know if that's not the product that they're buying? I mean, are they idiots for buying something that you say doesn't exist? And he's like, oh, Google is just doing a PR thing. And I was like, so you're telling me Google actually needs more marketing? So I just didn't find that particular occasion to be compelling, but I found it highly curious. But on occasions like this, I see the wrestler coming out in you, I have to say.
Well, the thing is, it's kind of like, you know, I used to care a lot about this kind of thing because I felt like there was maybe something that we were missing, and that maybe you try to peel back these kinds of statements and find substantive criticism. And I'll tell you what, it's exceedingly rare that in any of this kind of debate, anybody ever mentions anything at all that's an actual useful comment, which is remarkable. So, you know, you can go and talk to people and say, oh, they don't have anything quantum. I mean, how is that a useful comment? Because what ends up happening is when you ask them, well, did you read this paper? No. Well, why do you think that? Well, my friend said it. Well, how do you know that he's right? And it's like this thing where everybody's friend said it. And when you try to trace back what the origin of these things are, I've done, because I'm the CTO, right? Mm-hmm. So part of my job is to make sure what we're doing makes sense. Yeah. And the use of the academic community as a source of potential issues in the technology we're building is very important to me. And what ends up happening when you try to trace these things back is it ends up being some ridiculous side comment made by somebody who knows absolutely nothing about what we're doing that then somehow takes hold and people say it over and over. But the thing is that all this stuff is just noise. It's going to go away. It won't go away immediately. It'll go away in 2 or 3 generations once, we're selling, $500 million a year worth of this stuff. Mm-hmm. It's going to be very hard to continue to make these ridiculous, silly arguments that have no basis in fact. So now the way I look at this is that it's more the interesting thing about this to me is not anything to do with technology or anything. It has to do with human nature and sociology and how the internet changes discourse and understanding of topics. Mm-hmm. Because the internet is like it's like a positive feedback amplifier. Whatever you put into it gets blown up into something that's way bigger than it originally was. So if you say something good, it gets multiplied into this thing that's way better than you originally thought it was. If you say something bad, it also gets multiplied. So this affects people because most people don't have the ability to go and read the original material or to be privy to the details of what's actually going on inside Google or NASA or Lockheed Martin. So they depend on outside experts who themselves are, dare I say it, not unbiased. A lot of these people who claim that they're unbiased and are saying things that about the project, they have their own axe to grind. They have their positions and reputations to defend. A lot of these people have said really, really dumb, silly, provably wrong things over and over and over again about this project. And now they're in the position of figuring out how to get out of all of this ridiculous mess that they've created for themselves. And it's hard, because you have cognitive dissonance. If I've said something is wrong 18 times in a row, and then it's very clearly not wrong, what do I do? If you're a good scientist, you say, okay, I was wrong. But oftentimes these people are not good scientists, and they'll continue to hold to their earlier statements, even though they're completely ludicrous and wrong.
Do you feel sometimes in a way like Charles Babbage trying to make his difference engine, which was probably 100 years or, 150 years before its time? I mean, the design was there. He just didn't have the materials. He had brilliant vision. He didn't have the technology to put it together.
Yeah, there is I don't know if I'd want to put myself in the same camp as Babbage, because realistically, my role in this is not to actually do anything. It's to find people who can. So my role in the company is a team builder, not an actual implementer of anything. The people who are implementing these things are the Charles Babbages. But there is a somewhat of an analogy, because the things that limited him actually making that thing real were not theoretical things or blueprint type things. They were, like you say, materials issues and fabrication issues. And in our case, the thing that bottlenecks our progress is the same. It's materials issues and fabrication issues. They're of a different sort, but it's still the same idea. If we could build, if we could actually manufacture a chip with 1 million qubits on it today, we could have a 1 million qubit processor in 3 months.
Yeah, because that goes back straight directly to David Dalrymple's point about the biggest hurdle, and which you said is precisely the manufacturing of those chips.
Yeah.
How do you make them real?
So I think just like the difference engine, I think in 50 years from now, when people have like basement 3D printers for superconducting electronics, people will as hobbyists hobbyists some of the early D-Wave designs in their basement and operate them, just because it's sort of fun to go back to the old days and think about those guys in the early days of doing this.
Mm-hmm. Just like we did in the 90s with the original Babbage design, I might say. Well, Geordie, we've been here for a very long time, 100 minutes. I think, and I would dare to take your time only for the next maybe 20 minutes or so. So I'd like to move on to the technological singularity and related issues here. So let's start by, what's your take on the technological singularity?
Well, yeah. So this is obviously a complicated thing, but I sort of take the view that if there was a singularity, it happened a long, long, long time ago. You know, if you ask if there was a special point in the development of technology, it was quite a long time ago. You know, I don't know if it was hundreds or thousands or hundreds of thousands of years, but some part of me feels like the first time a human picked up a stick and hit another human over the head with it, that was probably it. Because as soon as we started using tools and we had the ability to communicate abstract concepts to each other in a meaningful and efficient way, there's a steady progression that has to happen. So you can ask yourself, could you have a stick-wielding, language-using primate that eventually wouldn't build computers? I have trouble believing that's true. I think that any stick-wielding, language-bearing primate, as long as they don't go extinct, will eventually build computers as a matter of something related to the fundamental laws of physics. Mm-hmm. And I think that's very difficult to imagine that not happening if that primate species continued to evolve and maintain its treasure trove of knowledge over time. So I think that the progress of technology, I think, is something that has been going on for a long time. Now, recently, like over the last 100 years, we've entered into the stage where the exponential is starting to become faster in its growth than the generation of a human, like how long it takes a human to live. Mm-hmm. And obviously that looks to us like a special point. But I think it's just the same thing that's always been going on. It's just now the speed at which it's happening is at part of the exponential where it's overlapping with our own lifetimes. And so the question about what happens next, I think that the conventional view of the singularity as the technology kind of maybe existing on its own, independent of us, I think that's already happened to a certain extent. So this other sort of maybe hardcore version of the singularity, like, is there a point at which humans become dwarfed by or taken over by or controlled by their technology? I believe we're already past that. You know, I think that the existence of things like mobile phones have become such a compelling and critical part of modern life, at least in the Western world. It's very difficult to imagine turning everything off. Like, I've asked people once, could you imagine going for a month without looking at a screen and what that would look like? You know, where would you have to go in order to go for a month without looking at a screen? And could you actually do it? And it's an interesting exercise because the initial reaction people have is, yes, of course I could. Well, how? Well, I'd go up to a cabin in the woods somewhere for a month. Where are you going to get your food? You know, so I think that we've become, to a certain extent, vectors for the proliferation of technology. So this is not obviously my idea. People have talked about this a long time, like Kevin Kelly and people like him, that there's a not silly idea that humans have become the transmission vectors for other forms of life. If you care to think about cell phones and cars and computers as forms of life, and our role now is predominantly to aid in the reproduction and evolution of those other forms of life. This is a weird way of thinking about things, and people are obviously not comfortable with this. But just for the joy of the mental gymnastics, imagine if you think about cars as being the dominant form of life on the planet, and then you ask, what is the role of humanity in promulgating those cars? It's a little bit like the relationship maybe between flowers and bees. You can't have one without the other. Humans can't exist on this planet without cars anymore. They just can't. You might imagine that that's wrong, but you'd be wrong. It's just never going to happen. There will always be things that transport us with wheels. It's just going to always be the case. And cars can't exist without humans. So I think that the relationship is much more a symbiotic one, much more like bees and flowers than it is these are just dumb pieces of inert metal that do our bidding. Now, let's go to the next stage. The actual thing that most people think of when they hear of the singularity is ultra-intelligent machines that make themselves better at a faster rate, et cetera, et cetera. That I don't really have anything to say about. I think that it's very clear that machines will become like humans and will surpass humans in every respect. Anybody who doesn't think that's going to happen doesn't understand the modern advances in AI It's imminent. In fact, I think that if you were to put all the pieces together, you could do it now.
Mm-hmm. Let me stop you here just for 1 second and jump in with a quote. But before that, I want to say in support of what you just said, I think the idea of us being the organs for procreation of machines has been around for at least maybe 200 years since Samuel Butler. Ted Kaczynski spoke about that. Donna Haraway in her Cyborg Manifesto spoke about that. Samuel Butler in the late 19th century wrote Darwin Among the Machines and spoke about that. So that's a very powerful idea with lots of people noticing it from 200 years ago. But going back to evolution and to intelligent machines, I want to read a quote and a daring prediction that you made at IdeaCity, which is the second thought that I've kept from you. And it goes like this. That's a quote from you. By 2028, intelligent machines will exist that can do anything that humans can do. Quantum computers will have played a critical role in the creation of this new type of intelligence. Mm-hmm. So I want you to unpack this a little bit for us, because it talks both about what we talked so much before this, and now it connects with the artificial intelligence moment.
Yeah, so this goes to my point that people don't appreciate how far along this whole machine intelligence and cognition stuff is. The history of science and technology is one of moving humans away from the center and putting them on the edges. That's happened always, ever, forever. Earth is not the center of the universe, and so on. And this understanding that the type of intelligence we have is not magic is growing. And unlike in the past when people were trying to build intelligent systems in ways that were clearly not going to work, the new ideas that have emerged about how to do this are sensible, I think. And they're sensible in a way that means that they can be implemented and tested and evolved in a relatively short period of time. And that will lead to machines having all of the capabilities that humans have, including creativity and spiritually questioning the nature of their existence and all of this thing. That will happen shortly. It will likely happen within our lifetime. And it will be, who knows what's going to happen when it happens. I think that's unclear. But whether it will happen is not a matter for debate. I think that it would be very, very silly to try to argue that it won't happen, given now our fuller understanding of what it is exactly that's going on inside our brains. That's not to say that all of the questions are answered. Of course they're not. If they were, we would do it now. But I think enough of the questions have been answered to be able to put together reasonable cognitive architectures, implement them in machines, and allow those machines access to the sensory data that we have, and the ability to process it the way our brain does, and therefore build what are basically a new form of life on this planet.
I agree entirely with you that there's, in my mind at least, no doubt about the probability or the possibility of this happening. I have a little bit more doubts about the timing of it, though. Mm-hmm. And I'm very impressed that you're sort of embracing, if I'm correct, the Kurzweilian timeline, if you will. Can you tell us a little bit more about why did you think that 2029 would be the year that we would definitely have AIs?
Well, I don't think that it's that far away. I think by that time, the technology will have been matured to the extent that that all of the repertoire of the things that humans currently outperform machines at, or the capabilities that humans have that machines don't, will all be gone. I think that the beginning of that is already happening, and that even in much shorter time frames, you're going to get things that make people very uncomfortable, like within 5 years. Mm-hmm. Some of the things that we're working on with our partners, I think are near that time frame. You know, within say 5 years from now, there will be things that we can do that I think. One way to characterize was they're going to make some people very uncomfortable about humanity's special place in the universe and the sorts of things that we still think are unique to us. And again, it's going to be a little bit like the quantum computer story. There's always going to be people who say, no, it's just a machine. But ultimately, that position gets harder and harder to argue as we unravel biology, we unravel the architecture of the sensory input and output that is connected to living creatures. We understand how the eye connects to the brain and all that stuff. And we show that these things are just basically doing exactly the same thing, except we built them. Mm-hmm. It's going to be very hard to argue that they're any different than us. And of course, they'll behave just like us too, or similarly to us. I don't want to fall into the trap of what most people do here and think that these machines that I'm talking about are going to be like androids that walk around that behave just like humans. That's not likely. What's likely to happen is that there'll be special purpose systems built in the short term that do something phenomenal that is very human-like. That's going to be the first thing that you see. Mm-hmm. And people will say, oh, it's not a human because it can't do X. And then it's going to be the old thing, the cartoon with the Post-it notes of all of the things that humans can do that machines can't. And they keep getting crumpled up and thrown in the garbage. And it will happen so gradually that people won't notice it until the thing does everything. And then people are going to go, what just happened? So that things like speech recognition, it's just speech recognition. It's just an algorithm. Or computer vision, it can recognize 20,000 things in an image, so what? It's just an algorithm. And then people are going to start putting these things together, and all of a sudden this thing is going to be crawling around on the floor and talking to you, and you're going to be wondering what happens. So I see it being this ineluctable progress of technology over time, people thinking linearly, but things actually being exponentials. The positive feedback that comes from the business side and the profit that will come from selling things that are built like this. It's going to lead to this. It's just a matter of when. I agree with you that it's impossible to predict exactly when, but the fact that it will happen is completely clear as long as, again, we don't go extinct, we don't do something stupid to our technology and our science and our ability to do it, which is still a possibility. It's possible that we could all not survive that long. But I'm very hopeful that's not going to be the outcome, but, it's a possibility.
I think it's definitely a possibility, and it's a caveat that Werner Vinge often says. He says, falling short of some kind of major disaster, like nuclear war or something like that, he also thinks that the technological singularity is pretty much guaranteed to happen within now, I think, the next 20 years, but falling short of that disaster. Anyway, you mentioned two words, the unraveling of biology. Let me ask you about this. Do you think that the brain is more like a classical or a quantum computer?
Well, all the evidence points to the being a classical device, but it's not that simple. So think about the brain as a piece of hardware that implements a bunch of algorithms. So if you buy that. Then the important part about understanding that system is not understanding so much the hardware, although that's an important thing. The more important part is understanding what it's doing. What are the steps that it's taking to accomplish its mission, which is an algorithmic question, which is to a certain extent separate from the hardware issue. So imagine the following scenario. Let's say that we understood the algorithms of the brain, and those algorithms involve solving optimization problems. Now, you can solve optimization problems on classical hardware. People do it all the time. But you might get a benefit from solving it using quantum hardware. And one of the very interesting ideas that's been floated is that if you were to run the algorithms of the human cognitive, not only the human, but basically all biological systems have the same idea, at least all primates. If you were to run those algorithms on a piece of hardware that was fundamentally better, what you might get is a sentience which is fundamentally different and better. So there's an idea floating around that if, in fact, the algorithms that are now believed to underpin certain aspects of cognition, which do contain a lot of discrete optimization problems, which is the sort of thing our chip solves, can be run on a quantum computer, the kinds of life or kinds of species that you'll get from that will be qualitatively better, in the sense that they'll learn things faster, they'll have deeper insights, they'll be able to predict into the future farther, they'll be able to take actions that have access to understanding that we don't. There was a short story called The Golden Man that Philip K. Dick wrote, and the Golden Man was this kind of mutant dude who could see all possible futures in front of him, but unfortunately didn't retain any of the information about the past. But that's kind of a side note. And when he was taking an action, he could pursue the perspective that was most favorable to him. That's in a sense what I'm talking about, is that if you could build an intelligence that had a deeper ability to speculate about the outcome of its actions, you might be able to get something that was qualitatively smarter. You might say, if you wanted to, it's hard to define intelligence, but qualitatively better to predict the future more effectively than any human biological brain could do. And as an aside, because quantum computers seem to require millikelvin temperatures, and there are none of those in nature, these things could never naturally evolve. So this is a very important point, is that if you imagine what life looks like in the universe, there could be no quantum computer-aided brains anywhere because quantum computers require millikelvin temperatures, probably.
Let me stop you right here, though. I recently interviewed Dr. Stuart Hameroff in Arizona. Now, the interview has not been published yet. But he has been working on the sort of quantum theory of consciousness together with Sir Roger Penrose. And during the interview, and I would have to find that reference when I finally make that interview public, but he was talking, I think, about a Japanese researcher who is doing a very interesting experiment showing that you can have quantum entanglement at room temperature.
Oh, yeah, of course you can.
And therefore, you could potentially have it in the brain, according to him. And therefore, and he argues that it happens in the microtubules of the neurons of the brain, which arguably are quantum entanglement. Now,
yeah, so
now they're the minority opinion out there, and they've been sort of attacked by all neuroscientists and quantum physicists alike. But what do you think of that?
Well, the fact that you can have entanglement at room temperature is a well-known fact, and anybody who studies chemistry knows this. You can write down the equations of a hydrogen atom or a helium atom, and the ground state's entangled. Entanglement is pervasive all over the place. That's not actually a good argument, because I think that the thing that you need to do quantum computation is a lot different than just having access to the resources. Whereas it's certainly the case that it's possible that a wide palette of quantum effects do actually occur in the brain. Of course, it's obvious because everything is quantum mechanical. When you have two molecules meet and they bind, that's a highly quantum mechanical process, and everything that exists in nature is kind of like this. What will a drug bind into a receptor is a question of quantum mechanics, not classical physics. Mm-hmm. Now, but it's a big jump to go from there exist quantum effects in the brain to the brain uses quantum mechanics algorithmically to perform its basic functions. And
he says for consciousness, so I don't know if he would agree that it's being used to perform basic functions. Probably his answer would be no. He would agree with you, in other words, because you can perform all kinds of things in your brain without being consciously aware of it, right? I mean, when you're under anesthesia, because by trade, Dr. Stuart Hameroff is an anesthesiologist. So when you're out, you don't have consciousness, but the brain is not silent. There's stuff happening there all the time, but you're not conscious of it. He says, though, for consciousness to be present, you need those quantum effects to occur.
Yeah, this whole business is so poorly understood now that it's very difficult to say categorically one way or the other. But I'm strongly of the opinion that the brain is a fundamentally classical information processing device, and that consciousness emerges from a very simple but powerful perspective that intelligence is fundamentally related to your ability to make a model of the world around you. Mm-hmm. Because if you want to think about why intelligence is useful, or why anything is useful, you want to be able to move towards your prey, grab it, You need to be able to move away from predators. You need to be able to determine which of the things in your environment is useful and which are harmful. And all of that resolves down to predicting. So if I have a model of the world in my head, I can run a bunch of experiments in my head to predict what will happen if, and then select among them the one that's most likely to be a good outcome for me. And consciousness naturally arises in that framework if your model is sufficiently complex that you can model yourself as well. So if I have a sufficiently rich model of the world, the nature around me, that includes myself, I'm conscious. So I don't see this as being any special magic. I think it's just a natural consequence of the obvious fact that intelligence is related to the ability to model the world. And I don't think that there's anything special about it. I think it emerges naturally from regular old-fashioned classical algorithms running on classical hardware. That's not to say that you couldn't make the thing much better if you ran the exact same algorithms on quantum hardware, which is what we're trying to do. Mm-hmm. But I just, even though I can't say for certain, of course, because, who can, I would be strongly in the camp of the classical hardware, brain being very efficient, special purpose classical hardware.
Yeah, I think that's by far the dominant consensus, both within the field of neuroscience, but also many of the sort of quantum physics people have been disagreeing with Roger Penrose, who, of course, is the quantum physics expert in that kind of quantum mechanical theory of consciousness. Anyway, Geordie, we've been together now for 2 hours, and I feel absolutely embarrassed to continue, even though I'm enjoying it immensely, and I've learned a lot. So let me ask you the traditional last two questions that I always ask. And the first one is, where can people find more about you and your work?
Well, if you want to follow as an interested observer, me and some of my colleagues maintain a blog, which is dwave.wordpress.com. So dwave.wordpress.com, which in the olden days, those of you who may have followed it for a while, it was more about my own personal thoughts than anything, but it's sort of become more about an exploration of some of the technical issues in actually using these machines. Mm-hmm. And we also have a Facebook page that has lots of interesting links on it, which is just D-Wave Systems Inc. on Facebook. Mm-hmm. So if you like that, you'll get a bunch of stuff about news stories and happenings and such. If you're a technical person that's interested in actually using one of the machines, you can contact the people who manage both of the publicly available systems and talk to them about running things on the hardware. So in the in the case of the NASA Google thing, they recently, I think it was yesterday, made their website live. There's a link to that website on the blog, and you can go there and go to the contact side and send an email to the guy who runs it, and you can apply for time on that machine, and you can even apply for joint. If you can get together a group of people, you can investigate some particular aspect of the use of the machine. And the thing with the same thing applies to the USC machine, although that one's a little bit more basic researchy. So if you're interested in applications and specifically in the machine cognition side, the NASA one's the right one. If you're interested in basic physics, the one at USC is the appropriate one.
That's fantastic for people to know out there. I was not aware that there was such a possibility. That's amazing. Now, the very last question I always ask is this. Is there a final message? We've been talking to you for 2 hours, which is incredibly generous of you. I really appreciate it. I know you're a very busy person and a father of 3 children. So what's the most important thing that you would like people to take away from our 2-hour-long conversation today?
Well, I think that the overall message that the project that we've taken on is a long-term one that has its sights on being around for an awful long time, and not to pay all that much attention to the issues of the day, because these computers are not mature yet. There's going to take some time to get to the point where they can be the sorts of things that you carry around in your laptop bag. They'll get there, but it's going to take a while. So that's one thing is you've got to be patient. There's a lot of this stuff that we don't understand, and the idea is that we work together with the best people in the world to try to figure out how they work, and that's going to take a long time. It's going to take years to make inroads into that. So be patient. The second thing I would say is that having worked with some of the top machine learning and cognition people in the world now for some time, is that those of you who are interested in machine cognition, machine intelligence, you should be happy to hear that this stuff is progressing really fast. It's progressing faster than you think, and that I think that the outcomes of these types of things will start to become more broadly available on shorter timescales than even you might have hoped. So that's a second thing. And just sort of on the third note, the becoming involved in something like this is not impossible. You know, if you have an idea, or you're a person who is interested in some of the things that we're interested in, we do work collaboratively with a large group of people. You hear about the big ones, but there are literally dozens of collaborative projects that we undertake. And one area that I'm particularly interested right now in is the generation of art using computers and machine creativity, is specifically in music, and potentially in more difficult to produce, usually human artifacts that are artistic and creative in nature. So if you're interested in the intersection of the artistic world and machine creativity, that's an area in which I've been looking very carefully recently for a variety of reasons. Mm-hmm. So if you want to reach out to us, feel free. You know, we don't answer everybody's requests, but if something particularly interesting comes along, we follow up on it, and sometimes they lead to deep and long-lasting collaborations and even friendships in some cases.
Yeah, as an interesting side note, I'm interviewing Stellark next week. Mm-hmm. So he has also a lot of interesting things to say about the sort of intersection between art, technology, transhumanism, and so on. But for today, I just want to say, Geordie Rose, thank you so much for spending 2 hours with us today. I really appreciate it, really enjoyed it, and I learned so much. And I'll have to go and re-listen to this multiple times to keep learning, because I think there's a lot of condensed content there that one can benefit from. So I really appreciate it. Thank you.
Well, you're welcome. Thanks for having me, and thanks for the listeners for the really good questions. And hopefully, I answered them in a way that was satisfactory, and that you enjoyed my 2 hours of ramblings.
Singularity.